Okay, so sorry for the snafu. So last time we went over a lot of material. Some of the main concepts that we saw, firstly, was we went into um, compressive sampling. Um, let me fix the So compressive sampling was this notion that um, we turn the problem into one of optimization, and intuitively the goal was that the underlying physical signal that you are measuring is being generated by some sort of a physical process which is sparse in some aspect. So for example, it may be a physical process which has a small number of parameters. So if I think of all possibilities of that process, then what we are really trying to do is trying to measure what the values of those parameters are. So the example I had was, imagine it was a sine wave, and so there are only 3 parameters. So if I think in terms of the parameter space, then it was very sparse out there. The other um, uh, uh, other examples where things might be, let's say, sparse in frequency domain because there are only few frequencies present. So compressive sensing kind of takes the approach that if I were to sample uh, much far less and then try to reconstruct the signal. So the example in case of sine wave was, if I actually go back, um, here. So the idea was that if I take samples and then I'm trying to find the values of phi and a, in this case we had assumed f was known, then in a sense if I plug in the, I'm trying to find that value of a and phi such that the estimates that I will get for the signal at the specified time are going to be close to what I have actually measured. So I have some sort of an error function and I'm trying to optimize it by finding the value of a and phi. And more generally, you'll have a larger number of parameters. And also, even in this example, we had seen that just even though we have 3 parameters, just doing 3 samples was not yielding very good results. So you need usually more, but a lot less than what might be needed with like the sampling kind of an approach. So the way this thing, the insight was that that made compressive sampling possible is that if I were to randomly select a set of samples out of a window, in effect, what we are doing is we are saying I'm taking a random projection. Then kind of the theory said was that with a very high probability, you would be able to reconstruct the signal back if you were to do an optimization where your goal is you basically say, look, the signal is sparse there, so the set of coefficients are going to be very, very few. So I want most coefficients, most parameters to be 0. So that's kind of the intuitive thing. Again, the rest of the material is way too advanced to cover in this course, but it has yielded kind of order of magnitudes type reduction in the sampling rate than you would otherwise encounter. The second approach was this of adaptive sampling, which is based upon the intuitive idea that you should not sample if interesting things are not happening. And we encountered it in this particular manner where we are going to look at, let's see, yeah, we are going to look at how much the signal has changed since I last sampled it, and only if it has changed sufficiently am I going to change it. Am I going to sample it? Now that obviously is only possible if you can monitor the signal in the analog domain without having to sample it, because we are trying to reduce the number of times you have to sample it. So kind of intuitively the way these systems work is that I have the last digital value that I sample. I'm going to take the corresponding analog value and then in the analog domain do some comparison. So the theory in case of control system suggests that if the signal current value of the analog signal is it has deviated from what we last measured by an amount which is larger than certain percentage of the current value of the signal, then we are good to go. So this requires an analog multiplication and an analog comparison. comparison. These things are doable with circuits. So that's one way to use it. The other way to use this concept is, let's go ahead and sample the A to D converter periodically. It's just that I'm going to discard some of the samples because I don't really need them. So every time I sample, I will check does it satisfy this test. If not, I will discard this. A third approach, which actually I didn't mention last time, is that I may have some sort of a model for the motor based upon current speed and acceleration. And so I will try to predict when, at what time would the signal change enough for this property to be satisfied. And then I'm going to schedule a sampling event at that point in time. So I continually kind of model and try to predict how long a step should I take. So deep down, these are all dealing with the rate at which the signal is changing, and then you are using that to drive the sampling process. So smarter sampling was one thing we spent time on. So these were just some animations. Then we had moved on to, and that's the topic for today, which is making inferences from sensor data. And I had started out by saying that, look, fundamentally, the role of sensors is that we want to estimate the state of something, the physical world, right? So, for example, if it's, let's take an example. Like a couple of groups are doing a project, gestures. So we're making gestures with hand, and we want to identify what gesture is it, right? So essentially, we are trying to find something about the sequence of states through which the hand went through when making that gesture. So, or likewise, existence of a disease. Let's say you're making measurement of, let's say, the physiological signals, the heart, the ECG signal, and you're trying to infer whether the heart is suffering from some sort of an arrhythmia, let's say, or I don't know, trying to detect whether someone has fallen. All those kind of things. So fundamentally, it's about state, and sensors are kind of a window into the state. There are two types of sensors: sensors which tell the system about its own state, and sensors, extroceptive sensors, which tell about the outside state. And sometimes some sensors can kind of do both the things. In order to make that inference as to what state the process is in, the system is in, along the way you kind of face some additional challenges, which require kind of almost in any system will require one to kind of deal with these things. So I had the example of a light sensor as kind of a very simple example of sensor, and it can be used to measure a variety of things, variety of pieces of information, which in turn could say something about the state I'm interested in. So, like for example, it can be used to measure the intensity of light. Now, the reason intensity of light may be interest, maybe, for example, maybe I'm trying to infer whether the person is indoor or outdoor, or maybe I'm trying to infer because I'm the one shining the light and looking at the bounce back light, how far away is the robot from a wall. So the same sensor under different conditions may be providing information about different states of interest. And then kind of within this umbrella of light sensor, there are also different wavelengths that it might be tuned to, directionality, all those kind of things that come into play. So the key point, remember, then, is that sensor measurement itself is not the state. Sensor measurement tells us it's about some aspect of the state, and hopefully by looking at the value of that sensor and perhaps some other sensors, you can get to what an estimate for what that state is that is of interest to you. So I may be interested in, is a person sitting on the chair or not? I may have sensors. It may give all sort of things: light level, color, something touching something, a level of sound, stuff like that. And all of them perhaps are saying something about the thing. In fact, world is pretty rich. So almost any sensor picks up something about everything. And it's really a matter of algorithms to kind of then infer things back. So I'll give a couple of examples of what I in recent years have encountered as kind of, I think, pretty cool examples of how the most unlikeliest of sensors can tell you something. So one example, this is some work out of Stanford, which is your smartphones. They show that battery thing, how percentage of battery it is, right? And usually apps can read what how full the battery is whenever they want. So an app can monitor that. From that, it can get the slope, so it can see what was the power consumption, so how how much power was being consumed. Then it turns out that on the phones, a big part of power consumption really is the cellular radio, because we talked about it earlier also, long distance radios consume a lot of power. Cellular radio, the power they consume is a function of distance. We again kind of saw that when we talked about the radio, d to the power n. Where the cellular base stations are located is reasonably public knowledge. So now you could basically try to fit this information you have, that you have something about the power consumption, how the power consumption is changing, with known locations of the base stations, and also map information is publicly available. So what this group showed was that they were able to find how a person in a vehicle with a cell phone was moving, where was he or she, without actually knowing data from the GPS. So they were getting the location from the battery level. Okay. Another example, this is from my own group a few years ago, barometer, which is in cell phones. It is there, I mean, among other things, it tells you the air pressure. Air pressure changes with height above the sea level, so it tells you about the altitude. So as you move around with a phone which has barometer, you are actually getting how your altitude is changing as you are walking around. Okay, and again, topographic information about the world is pretty readily available, certainly for US. There's a government website where you can go and you can get this information. And now again, it becomes a problem of some sort of a matching problem. That is, I have to take this altitude plot that I got from barometer and find out where would it best map to on that topographic that we have. So I can infer location. So there are plenty of examples like these where sensors, which, if you think about it, they can actually serve. They can serve as a proxy for a lot of different kind of measurements or inferences that one can make. So sensor one has to take kind of a very broad view of things. I talked about measuring distance to an object, so there's a whole bunch of things, and then you get some other stuff that radars and all that one can use. Detecting people, again, a very commonly encountered capability for security systems and all. You could use a camera, you can use heat, temperature, PIR, you can detect movement, color, distance, color because of clothing and all. And oftentimes then, depending upon your need, kind of a simpler sensor might be sufficient as well. Okay, so those are the final example at present was that this work out of Washington State, where these guys were trying to monitor what are called as activity of daily living. It's actually a very commonly it's a very common thing that many research groups kind of study. Variety of uses. Part of the use is we can create smart homes. So if the home can monitor what you are doing, then the home can adapt. The appliances and the lighting and all can adapt to it. There are also sort of assistive roles out here. So old people and all kind of detecting falls and stuff like that. And then safety, security, those kind of examples. So what people usually sort of approach this problem is, one is that we sprinkle or embed sensors in the environment, and kind of the walls and the light switches and the floors and furniture and stuff like that. So you see kind of a whole long list of those things out here. So passive infrared sensors, these you see like on the wall out there in security systems, they basically have a IR detector, and then in front this kind of a art type thing that you're seeing is called a Fresnel lens. And essentially what the Fresnel lens does is it basically collect light from a broad range of angle and then kind of narrow it down onto where the detector is. So essentially what you have is a detector which can collect light over a large area, and in fact to make it narrow, focused, usually just put light coming from something. So that's what PIR sensors do. They look for IR emissions, which is basically what body heat is. So, and in particular, they look for changes in it. So that's why they're called motion detectors. The reason they look for changes is because so that you can subtract out static heat sources, sun and stuff like that. Okay, so you look for those changes. Magnetic door window, they are super simple sensors. I'll show a picture of them out here. Again, I'm sure you would have seen these things. And then basically, when the door closes, the magnet comes close to the sensor, and vice versa. Vibration and pressure. Camera is a pretty versatile sensor. Historically, there are two dings against it. One is it needs a lot of computing, but that has begun to change because now you have sort of vision processors and things like that that have made things very cheap. And the other issue is privacy, which is we kind of get spooked by a camera for much more so than we'll be spooked by some of the other sensors. Microphone is another kind of privacy-intensive sensor, privacy-sensitive sensor. Electric meter and water meter, these are pretty cool too because by looking at the power consumption traces, you can learn a lot about what is happening activity-wise because different appliances have kind of unique signatures in them. Sensors on body is the other alternate part, complementary part. The usual inertial sensors and a whole bunch of physiological sensors that can that are used. Just to give you an example of kind of things that sort of we do. So like there's an ongoing project in my group. We're using kind of wrist-worn device. What we are trying to infer is computer usage, in particular typing behavior. So what we are doing is we're working with, this is a study about workforce performance. So we are using sensors in smartphones and wearables to make inferences about the emotional state and sort of broader internal state as well as productivity, because they all kind of feed into the workforce performance. So like a worker who's stressed or maybe distressed somehow may not be doing his or her job properly. So we want to kind of monitor those. And the usually standard psychological tests which are used, but they're used kind of very sporadically. So the goal of the project that we are engaged in is, can we do it continuously? Now, there are many different ways when someone is distressed can manifest itself. One of the ways may be you will drive rashly. Another might be you may be speaking differently. The one which my student is focused on as part of the larger project is typing behavior. So like when you are distressed in the way you type changes, the type of words you use changes, maybe your computer activity will change differently. So we are basically trying to see what can we infer about your typing behavior. Now there has been some work in recent years where people have shown, so just to give you an example, when you type password on your smartphone, every time you touch the thing, okay, the accelerometer picks up that tap. And people have shown that with the knowledge of the layout of the keyboard and given those accelerometer taps, they can figure out what password you were typing. More recent work has shown when you're typing password with a watch on your hand, by the signals here, they can figure out, again, knowing the way the keyboard is laid out, they can infer what password you were typing. So these kind of signatures which are always present. So as you might imagine, that for all sort of activity, eating, smoking, drinking, shaking hands, all these kind of stuff can be picked up through these. So that's what this group started doing, and they deployed it. It's a project called CASA, and it's been running for a few years. And they deploy sensors in space, and they have people wear a hip sensor and a wrist sensor in their particular case. And then you get these kind of signatures of activity. So this is how hand washing looks like. So you could see that there is activity at the kitchen sink, which is where a lot of stuff, and then the kitchen closet. So presumably the person takes out something, I don't know, towel or whatever, and then you see some signature of it in the gyro and the accelerometer on the hand and the hip. And if you look at the sweeping, that's kind of now different. So here you kind of see motion sensors which are getting kicked in. you see kind of firstly the sweeping activity kind of moves through the apartment, so you kind of see a temporal migration of motion sensors, as well as I guess there is a lot more back and forth when you're moving the vacuum, so you kind of see a much more dense signature out there. Now, looking at these, we can't say, I mean, if I were to simply show you this and say what activity does it represent, it would be pretty hard even for humans to kind of make any sense out of it. Unlike, let's say, images and all where we excel, but when it comes to sensory data, it gets tricky. I mean, maybe looking at these motion sensors, the way the pattern was triggered, you could begin to venture a guess. Inertial data is pretty hard to sort of make sense out of. So then, so what is sensing? When we say we are trying to sense, fundamentally, one way you can think about it is you have a system, and that system could be in many states. So let's say I'm interested in activity. So the state is what activity I'm doing, or more precisely, I guess we're calling it what action we are doing. Okay, so I would have my current state can take some set of possible values, right? So let's take some simpler example. Let's say we are interested in identifying what is my transportation modality currently, in the sense, am I sitting, standing, lying down, on a bus, on a bike, stuff like that. So at any given moment, you might, let's say, half a dozen options. So that's the state. And as every time step, so S0 is representing the state at time 0, and it would have one of those values. S1 represents the state at next time step, and again it would have some and the time step that you would pick out here would be something corresponding to how rapidly the state can change. So kind of a dual time, if you may, or it would correspond to like how rapidly things change. Okay, so usually for humans and all, human activity and all, tens of milliseconds is kind of a reasonable number that people often pick. Our speech also tends to be of that order, and sort of different things. So let's say 20, 50 millisecond windows in which I say the state changes, and so S0 may be sitting, S1 may be standing up because I was on a chair, I stood up, and then S2 may still be standing up, and then maybe, so there will be some sort of a trajectory that would happen in the space of possible states that I have. Now, unfortunately, or to make the problem interesting for us, there is no such sensor which just tells us whether I'm standing or sitting or running and whatnot. What I have is some sensor which gives me some measurement about that state. So it could be your hexaware, which is picking up these gyro and accelerometer signals. So what you get as the observation are the values of those sensors, which hopefully are capturing something about the state, but they're not directly telling me about the state. And the second thing is the sensors are noisy. So and then so these are our observations. So you can say whenever I'm in state standing, my sensors, having observed the fact that I'm in state standing, are emitting measurements, and those measurements are noisy, and they will be, so there will be some sort of a distribution that they will have. Like for example, whenever I'm standing, and presumably most of the time my hands are on my side, so the accelerometer on my band will probably have a particular gravity component, and then since my hands move around a little bit, when I'm simply standing, then again there will be some sort of a distribution around there. Okay, some sort of statistical distribution you might have. So that's what I'm seeing. So the task that we face with is, given these observations, we are trying to infer what is happening to those states, what was happening to that person, right? So that's why I call it sensing as a latent state estimation task. Latent means hidden. So there's a hidden state which we are not able to directly observe, and sensing is the process of estimating what that state is. Now, is this clear what's going on, right? So hidden state, we are getting some observations, we are trying to estimate that. Now, there are many simplifications that we do in this process, and couple of simplification number one is we do windowing. So while it is true that time is continuous and therefore you can say the state space is changing continuously in time, we kind of divide things into chunks in time. So we basically pick up something, like I said, 20 millisecond or maybe some appropriate window, and we divide the raw sensor measurements into windows over time. So our task, we simplify, we basically say that for each window, I'm going to predict what was the state. And this obviously runs into some conceptual problems like what if during that window I stood up, right? Or what happens? And again, the idea is hopefully you will pick a small enough window that the likelihood of that happening is close to zero. Okay, so we divide raw sensor measurements into windows over time. The other thing we do is we don't work with the raw sensor data. Instead, we compute a feature vector over that sensor data. So by feature vector, I mean we calculate some attributes of that data. So I have a waveform from each one of, let's say, the 3 axes of magnetometer, 3 axes of accelerometer, and gyro and whatnot. I'm going to compute some attributes of those. Why do you think you might want to do that? Like, why not work with the raw sensor data? More organized. Okay, more organized. What else?
The raw sensor data has long time service.
Has what?
Long time service. So
like more values, right? So it's kind of compressing things down. I'm looking at only some things of interest. Okay, so size. So instead of a long vector or vector with lots of entries, I'll have a vector with fewer entries. What else? Like just think about it. Let's say even if we take 1 second window, okay? 1 second, if my accelerometer is being sampled at, let's say, a kilohertz, so I have 3,000 samples from accelerometer, and I have, let's say, 3 inertial sensors, so that's a total of 9,000 kilobytes or of that order of data just from a second. Okay, so it's a fair bit of data if I were to be looking at that window. So features looking at only a small number of attributes can help there. What else do you think can benefit of doing features?
There's probably more variation in the actual data.
Okay, so you can clean things up, hopefully, I guess, yeah. So that's, what else? What challenge do you see if you were to be writing something which is supposed to run on a wide variety of platforms out there? So one challenge, another challenge you face is sensors differ, right? I mean, Hexaware has one accelerometer, Apple Watch has a different one, and Android Watch will have a different one, right? So the sample rate may be different, their calibration parameters may be different. So by going into the feature space, you unify things so that everything above that is just working on those features. And we separately handle how to go from raw sensor data into that feature space. So it makes things uniform. There's also, yeah.
The question of the feature space, so wouldn't other parameters also affect the feature space? Like for example, let's say you have an accelerometer on your hand versus one on your foot, right?
Sure.
Even though eventually they'll both be mapped to like some grams or some g value, right? Acceleration, but they can represent two different things. Or they can
Sure. So I guess bring out an excellent point, which is just because it's an accelerometer doesn't mean it's kind of same thing. So also matters where was the accelerometer, right? So its position on the body, and also this is usually the contextual data, and that can also be part of the features. Okay. So one of the feature for that window, but would be where was the sensor. Now, obviously, in your example, that particular attribute is not going to change much unless occasionally things that happen are like, I mean, one thing again we encounter it for the wearables. Sometimes people wear on different hands. Okay, they are yeah. So those kind of things are worth keeping. Some people like to wear wearables in their dominant hand. Others do it the reverse, and then of course people are left-handed and right-handed. So those kind of things come into play. For certain other items like take your phone, right? The phone is sometimes in the pocket, sometimes in the hand, sometimes maybe on the console of your car or stuff like that. And yet we are trying to make the same inference. So the position does matter, and that kind of contextual data is another feature that one would need to have. Features are also privacy friendly, which is instead of sharing the raw data, we are sharing something less, and therefore hopefully there is less concern about it. This is particularly important for acoustic signals because if you share the raw acoustic signal, that's essentially capturing everything you are saying. On the other hand, if you're capturing some features, and we'll see shortly what kind of features get used, yeah, it's kind of usually from features alone, it's hard to go back and reconstruct it. So friendlier. And then the idea is that we are going to use those feature vectors, a collection of attributes, as what we are going to work with after that layer. So we make the problem simpler in sort of in a variety of ways. Another simplification which is often done is that we will is often assumed, and again, obviously not um, it's almost never true, it's an approximation. Okay, is that independence across windows. Okay, and what this is saying is that we are saying that we have selected that what we are going to observe in window number 1 is independent of what happened in window number 0. And okay, so basically statistical independence. And what that means is that I can therefore make an inference by just looking at the feature vector from this part and not worry about what happened previously or later. Again, not true. Like for example, if you knew that my state at 0 was lying in the bed, it's very unlikely that state 1 is going to be bicycling, right? I mean, there's certain things which are statistically just never will happen. So while not true, to keep things simple, that's often done. But there are ways to address this also. Let's say I do want to account for what happened in the previous thing. Well, one thing we can say is my feature vector will also include information about the features from the previous window. So I just make it kind of larger. Of course, there are limits to it. I mean, because if you take into account the entire history, then you have a problem. But certain amount of things you can. And there are lots of examples where what's happening now is dependent upon what happened just previously. Like for example, I'm trying to measure the light level. Well, quite possible, quite likely it will depend upon just what just happened, right? Particularly for some, like people try to, if you're doing it outdoor, what happened previously will say something about whether a day is generally cloudy or generally sunny. So you will take that into account. But nevertheless, this is. And finally, the third thing is that what are we trying to do? So classification and regression are the two broad things that get done. Classification basically refers to that my state is some sort of can be in one of is drawn from a set of discrete possibilities. And so in my example, like it was sitting, running, biking, stuff like that. So that's an example. There's a finite alphabet, finite set of values. And basically what we are trying to do is we are trying to say which one was it. Regression refers to estimating real value, a number. So like for example, what is the temperature? What will the temperature be in the next time step? These kind of things which are more numeric in nature, and they obviously lie on some sort of a number line, whereas in case of classification, there is no particular, just a set of discrete points. So our goal of sensing is, given these observations, I want to predict. Within this, there are a few other categories of problems that you encounter, and which again more advanced courses can talk about. So the problem of filtering says that given all the observations until a particular time, I want to predict what the current state is. So from time 0 through t, so this notation is s of t given observation from time 0 through t. So given the entire history of observations, I want to say what the current state is. That problem is called filtering. Prediction is given all the observation until some time t, I want to predict the state at a future time. So is the car going to hit the car in the front? Okay, so that's a prediction task. Smoothing means that given the entire history until now, I'm trying to predict something in the past. Right? And the reason this is of interest is that oftentimes, if you, in filtering, you are only looking at things in the past. Here, in effect, we are looking at things in the past and the future. And the reason is that oftentimes you can make a better estimate of what is happening by also knowing what happened later. So, for example, based until now, you kind of predicted I was running or jogging, but there is ambiguity. But if you know something about the future observations, can give you more confidence, and you can kind of go back. Or oftentimes, like another analogy, let's say I'm speaking, not very clear, some word you didn't hear, but at the time. But then after hearing the subsequent words, you can go back and fill it in, right? So knowing the subsequent words kind of help back. And same thing with sensing, knowing the future measurements. So that's called smoothing. And then finally, most likely explanation, which is basically saying, given all the observations I have, what was the sequence of states that happened? And that sequence of state, you can think of it like the sentence, or like a longer activity. With these observations, was the most likely explanation that I vacuumed my home, right? So any given single observation might not tell you, but the sequence would sort of help you stitch that together. So for all these problems, there are all sort of approaches and all that exist. The simpler version, which gets used very rapidly, is just this. Given O of t, what is S of t? Okay, that's what this simplification is doing. So it's basically kind of move away from all of these, because if it is independent, then it doesn't affect the current predictions. I can just focus on the current observation. So basically, the problem that usually as a first step you can attempt to solve is, given O of t, what is S of t? And nothing else. You have no prior knowledge, nothing else. That's all you have kind of focused on. And then we try to solve for classification and regression. So there are a variety of algorithms that exist, and there is knife-based, which I'm going to talk about today, linear classifiers, which basically say that my end result is a linear expression over the features that I have. Linear classifier with non-linear kernels, which basically say that I am going to include in my feature set some non-linear terms. So for example, let's say I had some value x, I will also add to my feature vector x squared and x cubed, and now I'll do a linear expression over that. There are things like more advanced things like support vector machines, decision trees like an if then else, perceptrons, it's kind of a precursor to neural networks, and nowadays all the rage, deep neural networks. So and a whole bunch of other techniques which sort of exist out there. All of them usually act on features. One thing which has begun to change with deep neural networks is that you don't construct features in many cases, you just use the raw sensor data directly. In effect, you let the network find out what the features are. A challenge with features generally is that how do you figure out what's the right set of features to use, and we'll see that very shortly, but neural networks kind of attempt to do away with it entirely. So before you start to make inference, you also have to deal with the fact that the sensor data that we're getting is kind of pretty messy. And if you were to simply use it as is, oftentimes you'll find you can't use it, or even if you use it, the results will not be that great because it has those things I mentioned earlier, noise, calibration issues, those kind of things. So I want to highlight a few of those issues and how we, what one has to do about it. So this first issue is simply that of noise and errors. Sensors are noisy, because our underlying electronics is noisy. I talked about earlier when I was talking about radios, that when radios detect a bit, they'll collect energy from the received signal, EB over N naught, so energy in the received bit, and then they made a decision that a bit coming in is 1 or 0. All sensors operate like that. They are monitoring some signal for a short period of time, and then they decide, is the value this or that? That's what they are fundamentally doing. Um, so what happens because of this noise and error is that we end up getting uh, sort of lots of uncertainty in the measurement that you are taking in. And a very common way to for a lot of sensors that we think about it is that the measurement noise is Gaussian. So let's say I'm trying to measure distance to the opposite wall. I take repeated measurement, I'll get some sort of a normal distribution. But that's not the only type of error that you may encounter with sensors. Um, Sensors also have bias. That is, they may give you a reading which just has a shift in it. So that's a different kind of error. So it's no longer, all the readings are just shifted by a certain amount, some delta. So it's an offset there. Sensors may also have errors where the spread may change. So like I may have sensors where if you think in terms of normal distribution, so in some senses what we are saying is where is the mean and what's the spread of the normal distribution. So uh, so 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 sensors are noisy. Um, and in case of uh, things like robots and all, what that results in is that if the sensors are noisy and the robot tries to even answer a simple question like where am I, kind of what's my location and all, it therefore has consequent uncertainty about it. And that oftentimes this uncertainty can kind of build up over time so that you cannot even be sure about the action. And in case of robots, things are even worse. Even actions are uncertainty. Let's say I command the robot to open the door. It will apply the force. Did the door actually open or not? The actions can fail also. So sensing, action, they all in real world suffer from uncertainty. So noise and errors are a big part of it. Most common thing that you encounter when we face with a lot of sensors is that you have to condition the signal that is coming in. That is, instead of using it as is, you kind of remove obvious issues that kind of occur. So the example which actually had come up earlier, way early in the course also, many of these systems have buttons, as shown out here. So there's a mechanical button which you press. In this particular case, when you press the switch, then the capacitor is shorted out, and so basically the charge across the cap is zero. Now the problem with this mechanical switch is that when you press it, it's a mechanical device, so it doesn't make a clean touch. It may vibrate a little bit. And likewise, when you release it, it again makes contact with, removes contact, makes contact. So if you actually look at the signal, it might look something like out here. That is, instead of a clean transition when the button was pressed, instead of clean transition from 1 to 0, what we see is it went to 0, came back to 1, went to 0, kind of a few times before settling at 0. And likewise, when we release the button, I will again deep down might see these things going in. And part of it is, yes, you should have high quality switches, but a lot of this is inevitable. So then becomes the issue that you can sort of clean this. And in this particular case, it's called the act of debouncing. That is, we will take some sort of a filter and OLS all these transitions into a single one. So like typically what is done is you will say, aha, I saw a transition, but I will actually assume that it's a real transition only if it remains stable for a while. Okay, if not, I cancel it. So you implement it using some sort of a timer in software. So we didn't worry about it in the previous homework because embed kind of deep down the hardware level, I think, takes care of it. So it gives you a clean abstraction. But in many systems, you may have to face with these things. There are other possibilities also, which is measures are noisy. So one very common thing which is done is to take median. So what we may do is we may take multiple readings and then take the median. Why do we take the median as opposed to average?
Because average is heavily affected by outliers.
Yeah, so average is heavily affected by values which are just totally wacky. Okay, so you don't want to take an average of.
But the general calibration, when you use gyroscopes or accelerometers, they take average over the time. The most of them.
Depends at what level you're operating. Okay, so even there might be cases where you are going to see outliers. Okay, I mean, I must admit that gyros are perhaps less susceptible to it. On the other hand, let's say you were talking about taking the Bluetooth signal strength. Okay, so those kind of things are very susceptible to outliers, and they're kind of taking a few readings and taking a median is much better approach called median filtering than basically simply doing averaging. So that's the front end signal conditioning, and oftentimes it is built into the sensor, so you don't even have to kind of worry about it. But at other levels, you may have to, like for example, if your system reports a speed or a distance which is totally out of whack, then perhaps best to discard it. There's another reason why sensors may give bad readings is because if some adversary is trying to mess with you. So, but we're not talking about that. Another issue which comes with sensors is calibration. So the challenge in calibration is that you are measuring some underlying physical phenomenon, and then you are reporting a digital value. What is the mapping between the two? So, what the reason it becomes challenging is that this mapping often varies with environmental condition, and it varies with sensor to sensor, not simply two sensors of different make or model number, but oftentimes for the same sensor, same model number of the sensor, just because they are manufactured differently, some manufacturing differences. So calibration refers to that mapping, and it's affected by manufacturing tolerances and environmental conditions. So it changes over time, it changes from part to part, and certain type of sensors are particularly susceptible to it. So for example, I don't know if you guys have ever encountered this, your phone may say, recalibrate the magnetic sensor. And in case of iPhone, it kind of have you move it in a figure 8 form. I don't know what Android devices do, but presumably something similar. And the reason for that is that magnetic sensors are very heavily influenced by exposure to strong magnetic field or presence of strong, large ferromagnetic structures. So that movement of 8 actually forces it to be exposed to the Earth's magnetic field in different directions and then recalibrate the magnetometer. So magnetic sensors are particularly susceptible. There are a variety of ways to kind of deal with this issue of calibration. One is to have a calibration process, like that figure 8 movement. Another approach which is done is that oftentimes you may have a reference signal whose output is known, or whose value is supposedly known, and then you correct for it. So like for example, in case of cameras, oftentimes you see is they make you take a photo of a white paper, okay, under so that they can calibrate things. So image sense, that's a very common way of calibrating image sensors. So they are reference color sheets to calibrate your monitor. So you can have a reference signal to do it. And a third one is you can have a reference sensor. So if you believe your sensor is not working correctly, then you compare its reading against something reference and then find that mapping. So calibration is an important thing, and a very common model which is typically used is simply a linear calibration thing. Okay, we basically said, look, underlying phenomenon, and these are linearly related because much of the circuit is amplification and some gain and stuff like that. So it's a linear structure, but it doesn't have to be. And in some other cases, like chemical sensors and all, the relationship can be pretty much more complicated, and you would have to rely on understanding what the calibration curve looks like. So for example, temperature and frequency of a quartz crystal are related in a cubic manner. Okay, Okay, so we know that, that's how the underlying mechanics work. So knowing the physics of the sensor can help you calibrate. So conditioning, calibration, and I guess dealing with the noise. The final bit is missing sensor data. And I've just picked up some random sensor traces from the web to show that it's a real problem that people encounter, these kind of plots where suddenly you'll see a line, some missing values of the traces. These are all kind of picked up from various sensor sources. Why do you think it happens?
Lost connection with the server that you're trying to keep.
Okay, so lost connection and the system wasn't doing any buffering and all, right? I mean, okay.
Maybe lose connection to the voltage.
Lose connection to a voltage.
During that time, it got disconnected.
Yeah, or overflow of some queue. Those kind of things happen. So the point, I guess, simply out here is this is part of life. I mean, in any complicated system, it happens. And in fact, there's a broader issue of data quality. So in many cases, look, a data which is not data which are not collected will never be with you because it's in the past. So very important in these systems to have design your software so that you continually assess, is the data coming in, is it making sense? If not, throw up a warning so that you can fix it. Because if you don't, then it's way too late. You cannot go back in time and replay the activity. So missing sensor data is quite important. Could you do something about it? Like looking at these things, could you do something about missing sensor data? Or what should we do? Like, yeah, so you can think of itself as a regression problem of sorts, right? So you can try to come up with, because the problem that we face is the following. So let's say I'm collecting 9 channels of IMU data, right? And let's say one of the channels we lost the data. Unfortunately, since rest of your algorithms were expecting 9 channels of data and this one channel is lost, so one approach is throw your hands and say, look, for that entire time window there where we have the lost data on one channel, I'm going to discard everything else also. Or you try to kind of gracefully adapt to it to do some sort of an estimation out there. So there are 2 very closely related concepts that come into play out here. One is interpolation, which is if I'm looking at these, so looking at the let's say this bottom right. So I know the trace before and I know the trace after, and I have this gap. I do interpolation. The other one is in multi-channel data. You also have the possibility of what is called as imputation. So imputation is let me just write it down. So so you have imputation and you have interpolation. These are 2 possibilities. Imputation refers to with the help of other sensors. So for example, maybe there are correlations, cross correlations between other sensing channels and this particular channel. So if I'm missing on this, I can refer to those. So between a combination of these, you can exercise some repair of the data. There are lots of situations that you face, particularly with variables, right? They get loose. So maybe the physiological signal is not being picked up because the watch is not sitting next to the skin properly. So you might want to warn and say, look, the system that the sensor is with. In autonomous vehicles, a big challenge has been that the lenses of the cameras and all get fouled by whatever dust and stuff like that. So again, they begin to affect things. There are calibration issues and all that they also face because there's tiny little movement. Some of these cameras and all set in places where even you might think it's an imperceptible shift in its location, but it might actually totally make the computation being done out of whack. So missing data. So calibration, missing data, signal conditioning, and noise. Okay, these are all kind of things that one has to deal with very early on. Okay, so now after you have done all of this, then you come to the task of making an inference. So let's go back to that example from Washington State. I have motion, kind of these environmental sensors, motion, door, window, stuff like that, and I have variables. And with this, we want to now make an inference about what was the activity being undertaken, in this case, sweeping. So from going from data to inferences, as we kind of saw earlier on, we went through that intermediate phase of features and all, so we want to dive into that a little bit to see, but let's do a 5-minute break before we continue. So yeah, 5 minutes and let's start.
Did you try that one? Because the extra one's broken. Just a library that. Where did it go? Where does it? Somebody else wrote it. You just import that library. Well, yeah. Max 31. But I can still work.
Yeah.
Have you ever gone embed CLI to work?
Yeah.
Okay. Which
I did it early in the quarter. I haven't used it recently, but and I mean
which tool chain do you use for compiling?
I went with I downloaded the one from ARM actually.
Isn't that one not free?
No. They have a free version. They have a free version, and then I was using the Microsoft Visual Studio blah 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 the light version that as the editor with that. Yeah. So I did not go the Eclipse route, which is the other one. But yeah.
That to be able to use your own IDE.
I was just doing it for the heck of it. Yeah, and it's not so much the IDE part; it's the debugging part actually. That's really the main win. So there is something called I forget. There are two different ways that the embeds roughly fall into two categories of devices. There, one use something called open something, and but these are basically debuggers so that you can set breakpoints and all. And I was able to do that, so it worked to that extent where I was able to run things, set up debug points, and have it working. The only thing is that I was doing it with the other embed that we were using. Remember? Okay, I didn't do it with Hexaware, but probably should work. Okay, let's restart. So finally we are on the how to go from we have cleaned the data, calibrated and all. Now we are going to the inference phase. So first thing to realize is that generally speaking, we encounter two types of sensors in terms of type of data they produce. So there are sensors that generate events, and there are sensors that generate periodic measurements. And the difference between the two is the following, that events are really change in the underlying value. So like for example, an event may be the temperature exceeded a threshold, whereas temperature time series may simply be a periodic sampling or almost periodic sampling of the temperature. And you encounter both of these kind of sensors. So like for example, motion sensors that we encounter, they typically are event oriented. They send whenever they see a motion, and otherwise not. So they kind of see transition from no motion to motion. Okay. On the other hand, accelerometer, gyro, these kind of examples typically are numeric time series. But actually, most of these things at the hardware level are also capable of event-oriented stuff. So you could basically set threshold, and the accelerometer will not report anything until the value exceeds a certain threshold. So you can kind of operate them in these hybrid modes also. But for our purposes, you can say sensors which send reports asynchronously at times when some interesting thing changed, some event happened, and then sensors that just sample and keep sending the values. And when it comes to making an inference about the state, so now from that observation, you want to go back to the state. So one approach to do this thing, which works fine if what your sensor is reporting and what state you want to infer are pretty close to each other, is to simply use what I basically would term as a physics model. Okay, so what I mean by that is, if I want to know, I don't know, whether the person is feverish or not. So we understand that from biomedical literature that temperature above whatever 37 point some degrees Celsius are feverish state, and therefore we can just use that. So there's a very easy way to invert sensor reading into a state there. But most of the time that's not the case. Most of the time you have to do something more complicated. Now, even in those cases, you can use physics. So I'll give you an example. A very common thing which is done is, very common type of sensing is sensing of location. And the way we sense location is by usually measuring distance to multiple known location points. So like for example, GPS operates by effectively kind of having distance to multiple satellites, and from that it measures the location. In that case, you're basically relying on the physics or the geometry of the problem and then trying to find kind of what's the best fit solution to it. So wherever the physics is known and its physical model is reasonably accurate, that's a good way to go because I mean, you basically are operating according to laws of nature, so to say. But oftentimes we don't know that. So in our activity example, what is the physical model which relates sweeping to those sensor values? We have no idea there, right? I mean, yes, in principle there is some physical model, but it is whatever it is so insanely complicated and obviously not known to us. So this is where the alternative approach, which is data-driven models, come into play. The idea is we say, look, there is some model, but it's so complicated that we are going to let the data itself define kind of, we'll take a mathematical function which is capable of mathematical formula which is capable of expressing lots of functions, and we're just going to learn parameters for this function, and we'll say that is our model. So we are going to limit ourselves to some category of mathematical functions, and then we convert the problem to one of finding its parameters. So this is what is data-driven model, which is let the data define the model as opposed to something coming from our knowledge of physics and all. So this is what is broadly referred to as machine learning methods. So there are two special cases within machine learning. One is that I'm going to give you a lot of examples of x comma y. X is feature, y is activity. And after I've given you a lot of examples, you would have learned a model. And now, given a new x, you can tell me what the y is. So that's what happens in supervised. And in unsupervised, what happens is, I just give you a lots of x, okay? And you yourself would begin to, the machine itself begin to cluster them, okay? So the sweeping related x will hopefully lie in one corner and hand washing one in another corner. So this is discovering patterns and identifying ways in which things differ. And this requires that you look at the data at the right way, because if you just look at it in the time dimension, it may look very similar. So somehow you have to identify that some way of looking at the data gives me some patterns. Typically, machine learning algorithms, for reasons I alluded to earlier, do not process data directly. Instead, they use features. And the model that you use, how well it will do, depends very much on the features. And there are a couple of issues about the features. Firstly, your features should be expressive enough. That is, they should capture the relevant attributes of the signal. If your features are not expressive enough, then you are basically discarding that information, and you may never be able to reach a high quality decision. So for example, if the decision about fever depends upon core body temperature, and I discard that and have everything else, like whether you are lying in bed too much or not going to work and all, but you're missing that core parameter, then you will not do as good a job. So right set of features are important. Another thing which is that you don't want duplicative features. Okay, so think of features as like themselves as being little sensors. Each one of them is telling me something about the data. And if I have a biased set of features, that is, most of the features are telling about this one property of the signal, and then I'm getting duplicative information, right? So you want sufficiently representative features also. So selecting features is extremely important anytime you are processing, you're trying to make that inference out of them. So what kind of features might be there? So what you have out here is a trace from that deployment that I talked about, and what you see, this is kind of the underlying sensor data. So what you see out here is a timestamp, which is in the left column, so it's kind of identical tables on both sides. There is the ID of the sensor, so you see like dustpan, hip, on, hip, duster, on, hip, like that. So these are referring to different sensors. And And then what you see is that for sensors which are hip on these kind of things, remember these are the inertial sensors, so accelerometer, gyro, magnetometer. Here you see a tuple. Basically, you have 3 numbers for accelerometer and you have 3 numbers for the gyro. So there's a total of 6 degrees of freedom. So that's the measurement coming from there. And then the sensors at duster and all are more like event sensors. So whenever the duster is moved, there is a moved thing which is coming. So dustpan moved, then the hip sensors reported some values, arm, okay, and so on and so forth. Broom moved, what else? Motion sensor was triggered, MO70, hand soap was moved. So we're getting all these kind of events, and we are getting the data from gyros and all. So now we have to think in terms of like this is a sequence of what we saw in that duration of time. So now we have to think about how to go around organizing them into features. Do we operate directly on these, or should I convert these things into a feature vector and operate on that? If I directly operate on this, if I try to push all of this into a machine learning algorithm, A, it is way too disorganized, and B, it's a lot of data, okay, out here. So is there something better we can do about it? So some broad categories of features. So one type of features which are very useful are which are about the whole sequence. And couple which you can imagine would be very useful are time of occurrence. What time of day it is, what day of week it is. So for example, certain activities are more likely in certain time of day, certain day of the week. It's unlikely you will be sweeping on a work day, more likely you might do it on a weekend. On the other hand, I don't know, like washing hand may be more likely in the morning or evening. It's a certain time of day. So time of day, day of week. Another one is sequence duration, which is how long was that activity for. So certain activities are longer in time, certain activities are shorter in time. I mean, if the activity being reported is, I don't know, let's say it's jogging, we jog a lot less than what we might lie down in bed for example. So the duration of the activity plays a role. So these are features, as you might imagine, for the whole sequence.
So if we have a set of raw sensor data without any timestamp on it, so how do we apply time series?
If you don't have any timestamp, then obviously you cannot apply these features. Okay, you would still have a rate associated with it, without which the sensor data is totally useless. But if you don't have any absolute timestamp attached to it, then you lose that feature. Your job is harder. Now, these things are also important because let's say I'm trying to sense when people arrived in Bolter Hall so that I can turn the AC on. Okay. Without sensing, I can make a reasonable guess. Most people arrive at around 8 to 9 a.m., right? So a naive, stupid policy might simply look at time of day as a sensor, and you don't need any real sensor, right? So very important to, when you're comparing, you have to compare against what a naive policy might do, which is just making use of data that kind of like the prior information. So what's your prior model for that phenomenon, right? If a flu is going around, then a prior for that being a flu-related symptom kind of goes up, right? If so, your location may be another prior, right? I mean, if the location shows that you are, I don't know, let's say on a soccer field, then the prior that your activity might be related to running around or something goes up, right? So think of time, day of week, time of day, day of week, time of the year, right? I mean, there's certain things we do more often in whatever around holiday times and other times, right? So all those things kind of important. So this thing is useful information. Okay. Sorry. Yeah. So next one is characteristics of the discrete sensor values. So what I mean by that is these are those reports which were coming out, right? I mean, in the sense that in the table earlier, like each row, think of it like that. Okay, the duster thing, broom, like these are all representing reports. And one very common way of using these is what is called as bag of sensors. And this comes from an approach which became popular in document analysis called bag of words. So the idea behind bag of words is, so if I look at a document, it has words written in a particular sequence. Bag of words basically counts frequencies of the words. It doesn't care about the order of the words at all. Okay. So for example, document in which the word theater and is occurring a lot of time and movie is occurring a lot of time. Chances are that it's something about movies, perhaps a movie review or something like that. So if I simply were to look at the frequencies or rather relative frequencies of the words, it tells a lot about the topic of the document. So this bag of words, which basically says, let's ignore the order in which the words are occurring and let's only focus on what words occurred and how many times they occurred. It's the same thing out here. So if you see the dustpan sensor being triggered, it's likely a sweeping steady activity, right? So which sensors are triggering, which motion sensors are triggering are going to tell a fair bit about the activity, right? If the motion sensor in the bathroom is triggering, it's certainly not because I'm cooking. Likewise, if the motion sensor at the front door triggered, and then the motion sensor in the, I don't know, living room triggered, those kind of things might indicate, hey, I arrived home, stuff like that, right? So just by looking at this, what set of sensors and their relative frequencies, that's the bag of sensor approach can tell you a lot. And without, and in this case, kind of, we are ignoring the ordering and all, but sort of can be quite useful. So for that particular trace, you had a sounds for the different sensors, so dust time, duster, room, hand soap, motion sensor 17, 18, burner, and stuff like that, and we basically get the frequency. So that's essentially becomes a vector for you. And for complicated, remember we are after activities which are spanning kind of multiple time windows, so this gives us a good sense. Another one is elapsed time since the last event. By the way, again, I'm giving you these as examples. There is nothing sacrosanct about these particular features. In fact, feature engineering is really part of the task of designing a good system. What are the features you bring to bear your intuition and all into this? So elapsed time since last event basically says, how long ago was it that this sensor last gave me an event? So that's what you're seeing here. These are milliseconds over here. So it's basically saying how long ago was did it last happen. So this is another example of a feature. Finally, we have statistical features, which are defined over a window of time, and these are very well suited for time series where you have periodically sampled data, like the accelerometer readings and stuff like that. And I'm going to go over some examples of what we encounter. And the last one, which is, I guess, one of you had asked a question, contextual features. What was the previous activity I was engaged in? If previous activity was cooking, quite likely then the prior on that the current activity may have something to do with cleaning up goes up, right? Stuff like that. What was the previous dominant sensors? You may also incorporate information about features from previous time windows. All of these things can provide additional information for it to lead a better result.
So if we don't have labels on, I mean, assuming that none of the sensor values have no labels, so that we have the classified.
Mm-hmm.
So the problem would be approaches first regressing it and then classifying.
So in this case, we are not making use of labels at all, right?
Yeah.
So this is just the sensor values. So all this thing is saying is perhaps instead of looking at sensor values or features of sensor values just from the current window, I should also look at it from the previous window.
No, but how would we able to differentiate the features, like given that, okay, we are
we'll see how to make the inference from that. So right now, just saying that I have the features. Okay, we'll see how to use the features to distinguish between these things. That's yeah, we should get to one scheme today. Okay, so I have now taken these time windows and I have reduced them to various kind of features, and I want to spend some time on what kind of statistical features get used, because most of the sensors on Hexaware are like that. So there's a long list and by no means exhaustive, but there's some obvious stuff like max, min, sum, mean, median, deviation related stuff like what's the variance of the signal, zero crossings, various percentiles, histogram. That's a very good, you can just create some bins, histogram it, and that captures a lot about the signal. Asymmetry of the distribution, so formula like skewness and curotis, which are kind of formulated. Correlation across two sensing channels, autocorrelation within a sensing channel, how much energy does the signal have, right? I mean, like just earlier today, I was in a conversation with in one of my projects, and a very simple problem we are trying to do, I think, which actually can make for a cute little project if you guys, any of you still are short of project ideas. Am I wearing the Hexaware on the left hand or right hand? Just that. Okay. And a related question, am I wearing it on the dominant hand or non-dominant hand? Okay. Signal energy might kind of help there, as well as certain other things. Okay. And yeah, so a whole bunch of stuff. Time between peaks to peak. This gets used in physiological signals quite a bit. So those are some. And again, I can take that data trace that I described and I can compute all of these things for this table out here. Nothing magical about these. These are all little signal processing functions. You can do them very efficiently on Hexaware. Okay. So what this gives you is that this high rate data that you're collecting, if you were to try to get all of it out, then you would have a massive bandwidth crunch. But if you convert them into these feature vectors, then you would. Now the question, the challenge always comes is which feature vector? All of them? What subset of them? And that is where, unfortunately, you do need the raw data, and then you pull it into MATLAB or what most people like to use as a Python-based toolkit called scikit, and you play around it right there until you find the right set of features. Okay, so you do need access to some amount of raw data to be able to kind of play with these features. But once you have that, then your data is a lot. Your data are very, very compact. All the features that I had previously, they were about the time aspect. You can also go into features which are in the frequency domain, and three very common one is where is the centroid of the spectrum, what is the energy in the spectrum, and what's the entropy in the spectrum. And again, the formulas of them are given out here. It's basically they are all kind of giving kind of different aspects of the signal. And again, you can imagine they're kind of highlighting some different aspect of the signal. So, and there are all sort of other features that you might imagine might be useful, and obviously, needless to say, all sort of other sensors and sort of things around it. So, usually, a good starting point on what features to use is Google, see if anyone has done similar type of things and what features that they find useful. There are also systematic ways in which you can go around identifying things. So the way they work is you'll start with a whole laundry list of features. And then there are algorithms which can help identify what subset of features are explaining the data sufficiently. And then they will give you use this subset. The only thing is that it's a bit of a chicken and egg problem, right? I mean, I want to know which features to use so that I can use them in the model, but I don't yet have the model. So all these things which try to identify a good set of features are operating on some heuristics, and they are as good as they are. But they can easily discover things like, maybe these two features are really telling me the same thing. Why should I have both of them? I can discard one of them. So features that correlate with each other a lot are not good features. You should only have one of them. It's kind of like if I want a representative, I'm forming a committee and I of students, and if I just pack them with students who think the same way, then I'm not really getting any additional information. So you want features which are bringing out different aspects of the thing. So algorithmic techniques can help you there, and again, both MATLAB and Scikit have uh, methods to help you in that process. But uh, for most cases, you can start with kind of from some paper or something. What is the features? What are the features they were using, and kind of use them as a starting point for yourself. Before moving on to the actual inference algorithm, one other thing I want to also touch upon is you're never dealing with a single sensor. In most cases. Most cases you have multiple sensors. And the question that becomes is how do I make use of these multiple sensors as they are going together to help me make an inference. So broadly speaking, there are three places where you can combine the sensor data. One is data fusion. So this is best done when I have similar sensors. If I have 3 accelerometers, how should I combine them? Well, perhaps it's reasonable to average them because they're kind of measuring the same thing. So I average, we take feature vectors and they combine them. Maybe I can weigh them by some measure of how much I trust those sensors. Maybe the high quality sensor is going to get more weight than the low quality one, or how much variation they have. So I could use that. The second level is I could do it at the level of features. So in this case, I may have, let's say, 2 sensors. They are both telling me about the same process, but they're different sensors. Usually, what you do is you will simply concatenate the feature vectors. So, feature for sensor 1, feature for sensor 2, and then you just take a union of them. And then it may happen that some of those features, attributes of different sensors are overlapping. So you can make use of techniques like principal component analysis, which a couple of lectures ago we had a vague reference to. These are methods which can help identify those dimensions of the signal, of the feature vector, where promising things are happening, and discard the rest. And the final one is we actually don't do any fusion of sensor data. We actually make independent decisions from each sensor and then combine the decisions. So if that would be like each sensor is saying about the activity. The sensor is saying, oh, this guy is walking. Say, oh, the person is standing. Another one is saying, oh, this is walking. I can take these decisions and I can fuse them. I can use voting. I can do some sort of a weighted voting. I can go after which classifier is known to work best, give it more weight, and have another classifier which combines different decisions. So kind of have a second tier, perhaps a neural network and all, whose job is to take these votes and tell me the actual result. And then techniques which make use of Bayesian methods. So so whole bunch of approaches. So I can combine sensor level, I can combine feature level, or I can combine at the very end. All of these are different ways you can combine these things. Usually, for the kind of work that you would likely be doing, you'll probably be doing feature fusion. So you would have like the different sensors you're using, you're calculating features over them, and you're just going to treat them as part of a bigger feature vector. Now comes the part, now I have the features. How do I go around actually inferring the label that we are interested from it? So as I mentioned, historically, that processing is being done using a combination of physical models, EE type signal processing, and some heuristics. And for many cases, this is perfectly fine. Nowadays, machine learning methods get used for a couple of reasons. Firstly, they help us deal with sensors where the physics is, where the mapping from phenomenon to sensor observation is not very clear. Does the image have a person? Is the image showing a dancing woman? Is the right? All these kind of things are very hard to put in terms of a physical model. So data-driven models through machine learning are the ones which kind of help us out. And the example of gesture and what activity we are doing and all, they all fall into that category. There are, under the umbrella of machine learning, there are a whole bunch of different ways that you can learn a data-driven model. I have a laundry list of them out here. Most of them we don't care. The two that are important, and actually the one which is most important for us, is supervised learning, because almost all machine learning that takes place right now is supervised learning. But you do hear about these other things. In fact, in recent past 6 months to a year, reinforcement learning has been a lot in news. Reinforcement learning, kind of the idea is that the way the model learns is that it does something and then some sort of entity gives it a feedback saying how right or wrong it is, and then it changes its behavior. This is what went behind all these high profile systems which have beaten on chess and Go and playing Mario Brothers and doing all those kind of things, right? And achieving kind of superhuman performance at this stage because they're beating the champions and all. You really don't need any of this stuff here, or at least not for the kind of the stuff most embedded systems do. What we end up doing for the most part is supervised learning. But I'll mention unsupervised also because that's the close, another one. So broadly two categories in supervised learning and unsupervised learning. And the way to think about it is supervised learning is what we use for classifying things. There's like walking, running, whatnot. Regression, which is what speed is the person moving at. And clustering is under unsupervised, where the system detects patterns and then groups it. And then we can give it names. Oh, this group stands, there are 3 different kind of activities. Okay, we don't know what they are, but there are 3 different kind of activities. For us, it's the left side which is the most important. I think almost all projects that are happening in the course, if they're using machine learning, they're using this left side. Occasionally you'll find regression type where we are estimating speed or force or stuff like that, but and I don't think anyone is doing anything involving clustering. So I'm going to talk about how classification can be done using supervised learning. So the way the process typically goes forward is the following. There are 2 very distinct phases that you are going to be doing. There is training and there is prediction. Prediction is what happens at runtime. Training is what happens upfront. There are systems in which there can be continual training, but let's ignore those. So the idea is we collect some raw data, which we call as training data, along with labels. So let's say we were doing this thing about whether I'm running, walking, sleeping, whatnot. So you're going to go around, collect the data, and somehow manually label them, right? I'll say I went to bed at 7 p.m. and woke up at whatever 4 a.m. and stuff like that. Okay, so I'm going to label the thing, and you're collecting the data. Labeling is a very hard problem. It's a very labor-intensive problem. In fact, there is a quote that many people make that labeling is the blue-collar job of the AI era, because much of artificial intelligence depends upon availability of this kind of training data, and this can only be collected with a lot of pain. Some of the advances that we hear a lot about in recent years with neural networks happened because large amount of labeled data was available. And the way they created labeled data is using mechanical Turk. Anyone knows what mechanical Turk is? What is it?
Well, I've used it before to generate labels.
You have? Okay. So mechanical Turk is a service provided by Amazon where there is an army of unknown people who happily do boring tasks or whatever, happily do tasks. So basically what you do is you have a task to do. Yeah, usually these are tasks which would involve processing some data or filling out forms or surveys or stuff like that. So you essentially create a task. Very common thing is you will say, I have this task, and I want to farm it out. You're going to get 5 cents. So maybe the task maybe look at the image and label it, like is it cat or dog, for example. Okay, and so so what the worker, so you'll post this thing with the price and all, and what the worker in this mechanical Turk sees as a link. You go press the link. As a worker, you go press the link. You'll get an image. You say yes, no, that, you get your money. Okay, and you keep doing this thing. And apparently, lots of people sort of do that. It's pretty cost effective. People have done all sort of analysis about what's the quality, how long it takes to finish the task and all. But it's great for labeling. If you want to get images labeled or sound clips labeled or find spelling mistakes in a paragraph or stuff like that, they are all very well done using Amazon Turk. All you need is a credit card and you're good to go. Your standard Amazon account. Unfortunately, it doesn't work very well for the kind of sensor data that we deal with. If you throw those accelerometer traces at them, I don't think any one of them can make any sense out of them, right? So labeling works well for certain kind of tasks, but not for every labeling using Amazon. But let's say we have this label data. Then what you will do is you have also identified some features you're going to focus on. So you will do a feature extraction, and now after feature extraction, you have a vector of features, or what this figure calls feature matrix, but just vector. Now, the reason it calls it matrix is because I have a feature vector for every data out here, every data out here. Now you train the model. So what training the model means is the following. I'm going to say my model is a mathematical function and it has some parameters in it. And my goal is to find the parameters of the model which best fit the data. So imagine a mathematical function which takes an input data x, produces a label y. And my goal in this whole process is to find those parameters of the model such that they best fit the data. And there are lots of issues and all one faces out here, but let's say we are able to do it, we are able to do it in a manner which is good. Then what I have at the end of it is I know the parameters of the model. And the way you do this training is that you think of a set of parameter values, you see how well it does on my training set, and if it does bad, you adapt those parameters and you kind of iterate the process. It's an optimization problem, much like in compressive sampling that we encountered. Set of parameters, you're trying to find the parameter value. At the end of it, I have a trained model, and then I deploy that, and now in a runtime system, I have new data coming in. I'm going to extract the features, push the features into that trained model, and I'm going to get my label out. And the whole, so this is general supervised learning. The whole question then boils down to what is this model? What's the mathematical structure that we are going to use? What are its labels? And they can range from very simplistic linear functions to super complicated deep learning networks and all, and kind of a whole bunch of stuff in between. So I'm at the end of the time, so I guess I'll do the discussion section tomorrow also. Although I think Amr is out of hospital, but I'm not sure he has doctor's permission to yet sort of come. But so I'll likely cover, and I'm going to start with kind of perhaps the simplest way of doing this classification, which works pretty beautifully. It's something called knife base, and but also I'm going to describe some of the other systems. One thing to bear in mind is, given that this is such a hot area, there's tremendous amount of code floating around for everything. So you can create a good system without having to write much code because there's so much stuff on GitHub out there. So anyway, so we are going to pick up at this point where we'll talk about what are some of the models, what are their parameters, how do you go around learning them. Remember the learning part and all, this happens offline, right? You still have to collect the data, go offline, and then you write the code which is actually running in the system. Okay, so we'll see you guys tomorrow. I have my office hours. You can come and collect the, and actually there's some other stuff which also came in, which I believe is sitting in my office. So any of you expecting hardware, just come by with me right now and see if that came.
So we don't need our Hexaware reply.
Hmm?
we don't need to bring our accelerometer.
No.